So, anybody out there? Yes? Okay. All right, let's get going here. Kind of a dreary day to be out. But it's Friday. Oh. Okay. Well, I'll not, 3/4 of you are done, which is great. I'm sure the rest are very close. If you need help or you're stuck on something, you can post on Ed. Just make sure it's private if you're posting code. You have a question or you have an error you can't figure out. Okay. All right. So where are we? Always right here. Today we're going to talk about flip-flops. So we're going to jump into the world of sequential circuits. And you will need to use flip-flops for Lab 3 because you're going to build a counter. Okay, so Lab 3's posted. Lab 3 is a 1.5-week lab. So demo is not due next Thursday. It's due the following Tuesday. Okay, the next 3 labs are 1.5-week deals. You also have a homework due on Wednesday. You should be able to do it. You should be able to do most of it now. Problem 1, problem 2, problem 3, problem 5 you can do now. For 5, you're going to want to wait till after Monday. Okay. Any questions? No questions. Yes, a question.
After today, we will have all the information for Lab 3, right?
Theoretically, but I will talk about how to build counters specifically on Monday. So you may want to hold off on building the counter, or if you want, you can look in read ahead in the text. There are a lot of components to Lab 3. Let's go over it. Okay, so there's the counter themselves. Which will go. I will show you how to build a counter. But there's some other things that you're going to need, like an edge detector, ring counter, selector. You already have this from Lab 2. You have this X7 seg from Lab 2. So you could do a lot of the setup. I would put off actually designing the counter itself until Monday. Yes.
Even though it's not notated, the triangle in the counters means the clock, right?
Yes. So, okay, we're just about to talk about that. Yes, any component that has a little caret like this, that's going to be our clock input. That when you have a caret like that on a symbol, it means that it's sensitive to an edge or a change rather than the level. But for us, it's basically going to mean that's the clock. Yeah.
Outside of like the website and the textbook, is there anything else we should be referring to for like making Lab 3 and the other labs? Like, do we have everything that we need between like the textbook and
Yeah, you shouldn't need to. I mean, there's some other links within these pages that describe the parts. For example, we're going to talk about this, but here it is again. This is a little bit too early for us. We'll see that soon, but everything you need should be here, or linked. Okay, you shouldn't need to go look up Verilog anywhere. We're sticking to a very small subset. And that's to keep things simple and predictable. Okay, all right. Any other questions? Okay, all right. Let me change this now to, hopefully this will work. All right, so here we go. So far, we have been talking about combinational circuits, right? Combinational circuits are networks of logic gates that flow in one direction. There's no feedback. And they are memoryless. That is that once the new inputs have caused the outputs to settle, you have no idea what the previous inputs were. It's completely wiped away. So they can't remember anything about past inputs. Okay. We know that they settle. We'll talk about how you calculate when they will settle, but we know they will eventually reach a value and then not change, as long as you're not changing the inputs. Okay. As opposed to that, sequential circuits have feedback. They do recycle and remember stuff. So they have memory. And so we did a very small circuit that had a loop before. Remember this from the first day? Basically, if A is 0, then this is blocked. But if A is 1, then we have an inverter here feeding back on itself. And so this is like a Mobius strip. You go around and around and round and round, right? It just wants to keep inverting its input and feeding that back. So it'll never settle. But as soon as we stop A, this will hold a value. As soon as we make A go back to 0, this will just be some value wherever it stopped. So like a roulette wheel. Okay. So these sequential circuits do remember something about their output. Their output is influenced by the previous inputs, not only the current ones. And they have a possibility that they might never settle. They might just keep on trucking. Okay. So those are differences between these, and important differences. Designing arbitrary sequential circuits is really complicated and requires analysis at a very deep level, more than the logic level that we're dealing with. To make design of logic predictable and simple, we restrict ourselves to what are called synchronous sequential circuits. Synchronous sequential circuits are circuits that will only change in response to a clock event. So there's a designated signal, which we call the clock, which it's sort of like a heartbeat. And the circuit will load new values or remember based on the clock. Okay. So all changes are going to be synchronized with respect to this clock. Okay, and gates, we know our logic network will settle within this fixed time after the clock event. So one of the things we have to make sure is that we don't have too many clock events. They're not too quick. We need time between clock events for the rest of the circuit to settle, the combinational part, logic gates. Okay. All right. So this is a clock. We will, in this class, only be concerned with the rising edge. So the clock event that we care about in this quarter is only the rising edge. You may, in future classes, be dealing with circuits that react to the falling edge. There are some flip-flops that react to both the rising and the falling edge. Okay, and that's all fine. But for us, we're keeping things simple. So just the rising edge is the clock event. Only the rising edge will cause a change. Okay. So one clock cycle is the time between successive rising edges. And in this particular case, what is that time? 2 microseconds, right? We have a rising edge at 1, 3, 5, and I assume 7, etc., right? So this is a clock period of 2 microseconds. Frequency, how many of you have heard of hertz? Not the rent-a-car, but the unit. Hertz is just shorthand for 1 over seconds. And so sometimes clocks are measured in frequency rather than giving the clock period, and it's really easy to go from one to the other. Frequency is just 1 over the clock period. So we have a 1 over 2 microsecond frequency, which is otherwise known as 0.5 megahertz. If we had a 1 microsecond clock period, this would be 1 megahertz, etc. Okay. So I'm assuming you can all do the math, right? You need a calculator for this? Yes? I just want to let you know there will be no calculators on exams. Okay. But you won't need them. Okay. All right. So here it is. Yes?
Out of curiosity, even if we don't get calculators, will we at least get a list of what the different SI prefixes mean, or do I have to rememorize those from last quarter?
The SI.
Like standard unit.
The standard units, the micro versus pico versus...
You don't know those?
Well, I know them when I need
So,
them for class.
milli or kilo?
I know milli. I know like up to 10 to the 3 and 10 to the negative 3, but once you get to like 10 to the negative 12, I don't.
I don't think you need to worry about it.
All right.
We would accept 0.5 times 10 to minus 6 seconds rather than microseconds. Okay? Okay. All right. Basic memory element, the D flip-flop. Okay, so this is our memory element, and what we'll be using in our sequential circuits. It has 2 inputs. It has a data input, D, and it takes the clock as another input. And it has 1 output. The output is the value that it's currently holding or storing. Okay. When you want to have one of these in your circuit, you would just instantiate a module called FDRE. You need, as usual, an instance name for your module, so you'll invent a new instance name for each flip-flop that you introduce. If you have the same instance name, Vivado will complain. And then you have 5 ports, which is interesting because this one only has 2. Okay, so what's going on here? So these flip-flops come with 2 additional possible ports, which most of the time you will not use. However, you need to specify them. The .R is a reset, and generally you won't want to reset your flip-flops yourself. You won't need to. So set this to 0. There's also a clock enable port, and if this one is set to 0, this flip-flop will never load anything, and it's kind of useless. So you want to make sure you set this one to 1. If you fail to include either of these ports here when you instantiate this module, you're leaving it up to Vivado to choose. Vivado can choose to put 0s or 1s there. Now, often Vivado will do the right thing, but I've seen it do the wrong thing. I've seen it put a 0 here and a 1 here. And of course, then it doesn't work the way you want it. It's kind of useless. Yes?
Sorry, what does CE do?
CE is a clock enable. We'll talk about that in a minute. Basically, if this is 0, you're not loading anything, regardless of whether you have a clock or not. Okay. Oh, all right. Dot C is the clock input. The only thing that should ever be connected to dot C is the system clock. In all the labs, this will be CLK. Okay. Now, the other thing is you don't need to build your own flip-flops. This is already a library symbol. And Vivado has the library for all the parts. So it knows that the flip-flops are on the chip. And when you declare this, you're telling Vivado, hey, I want to use one of your flip-flops that's built in. There are thousands, tens of thousands of flip-flops already on the FPGA. You don't want to build your own. The Xilinx had done a much better job of building them than you could do with all the wiring that's there. So this basically says, hey, make a flip-flop and connect it as follows, or use a flip-flop, I should say, and connect it as follows. Okay. So let's talk about how this flip-flop behaves. Okay. Very simply, what happens is that at a rising edge of the clock, whatever value's here on the D input, that gets loaded inside the flip-flop. And that happens at the rising edge. So it's going to happen 3 times in this diagram. And then the output here is just whatever's loaded into the flip-flop. Okay, so initially, even though the input here is 0, we might not know what this flip-flop has stored in it because we just started up. Unless somebody tells you, hey, all the flip-flops are initialized to 0, you don't know. If you build your own flip-flops and you power on your circuit, it could be that those flip-flops wake up with 1s or they wake up with 0s. All right, so our convention is unless you've been told that the flip-flops wake up with a 0 or wake up with a 1, you don't know. So initially, the flip-flop output is unknown. Okay, at the first clock edge, X is 0, so what happens? Nothing? Yes? So Y goes to 0. Okay, now Y will stay 0 until at least the next clock edge. Now, okay, if you look carefully here, I made Y change after the clock edge, and I've probably exaggerated that a bit. But it's key to your understanding that those flip-flops, even though they load at the clock edge, their output doesn't reflect the value they loaded right away. There's a small delay. Okay, so that the Y output actually only changes after the clock edge. Okay, so what happens at the next clock edge? 1. Okay. What happens at the next clock edge? It loads a 1 again. So it actually loaded a 1. But as far as you're concerned, it stayed 1. Okay. So that's our basic element. That's how it works. It comes with a warning, though. In order for this flip-flop to work, you must keep the D input stable around the clock edge. There's a very small window of time around the clock edge in which D cannot change. If D changes during that window, then you void the warranty on the flip-flop. It will do all sorts of things. In particular, it could oscillate. which would not be good. Okay, so our circuits are going to be designed in such a way that we are sure that D does not change too close to the clock. Okay, all right. So that's the D flip-flop. And now we have the, how many are there? I think the 5 commandments of synchronous design. Now, this is to make sure your designs work as you expect. Okay, if you don't follow the rules, then you could have issues related to timing, temperature, environment, all sorts of things could affect or make your circuit not work. But if we follow these rules, the behavior of your sequential circuits is very predictable and will match the simulation. Right? If we have a situation where the simulation says one thing and the reality says another, it's very hard to get things working. Okay? If you go out and design circuits for a company, they will be very upset if you don't follow the rules and you create an asynchronous circuit, because it might work fine in certain test conditions and then change the environment, send it to somewhere where the temperatures are different, and it suddenly won't work. Okay, so, all right. All right, so here are the commandments. The clock input pin of all D flip-flops and any component that has a clock pin should only be connected to the clock. So there will be one signal designated at the clock, and we'll call it CLK just to be sure. You will be building components that have inside them components that have inside them components that have D flip-flops inside them. So it is okay to pass the clock to a component as long as each component only passes the clock to the clock pin of a component or to the clock pin of the D flip-flops. So if we were to flatten your entire circuit, we would only see that the clock eventually only goes to the D flip-flops. Okay, so sure, you can connect the clock to a component that's not a D flip-flop, but just only to its designated clock pin. Okay, the clock should never go into any logic gates. You should never see a clock going into logic gates, nor should you see any output of logic gates going into the clock input. Okay. Sometimes we will have external inputs that come from components that don't share our clock, and then we'll have to do something special. And we'll talk about that, how to synchronize an external signal. Okay. Let's see, what's the last one? Okay, outside of the flip-flops, you should never have any loops in your combinational logic. So we will have loops in our circuit diagram because the flip-flops, in fact, will be their outputs will circle back and affect their inputs. But if we were to take all the flip-flops out of your circuit, there would be no loops. Every loop would have to go through at least one flip-flop. Okay. Any questions on this? Yeah.
Could you re-explain to me what point 3 means? I didn't quite grasp it.
Okay, so you should not be feeding clock into any logic gate. So no AND gates, no OR gates, or nothing that eventually goes into an AND gate or OR gate. The clock should end up only going to clock inputs of flip-flops. Okay.
But inside the component, wouldn't they then probably go to a gate of some kind? Or?
Nope, they could only go to the flip-flops inside that component. But even though, at the top level you won't have flip-flops, they're buried inside a component, but effectively the clock ends up only going to flip-flops.
Okay.
Yes.
From what I'm understanding, does Rule 2 say that only one clock input should exist and should be passed on?
Only one source clock exists. We will be using only one clock in this class.
Okay, thank you.
Yeah.
This is a question for like an earlier slide, but you mentioned that the board has its own flip-flops.
Yes.
So I don't think this is going to be a problem for this class, but it is theoretically feasible to run out of flip-flops?
No.
No.
No. There's tens of thousands of flip-flops on there. You will not run out. Even for the largest lab, I think we use only 10% to 20% of the chip.
I see.
You are not going to run out of flip-flops. Now, 10 years ago, things were tighter, the chips were smaller, and if people were extravagant in their design, they could run out of stuff. Yeah. The other thing that happens is if you fill your chip a lot, it takes forever to place and route it, possibly overnight. But we're using such a small part that it runs in 5 minutes. I know you think that's a long, long time, but it's really not. Okay, all right. All right, so let's look at a very simple design with 3 flip-flops. This is a 3-bit shift register. We have 3 flip-flops in series, right? Our external input is A, and we have the output of the first one called B, wire B, feeding into the second one, and the output of the second one feeding into the third one, and then the output of the third one is the final output D. Okay, if I were to write this in Verilog, it would look like this. Right? I would instantiate 3 different flip-flops. I'd invent some names for them. I could call them Mo, Curly, and I forgot. What? Larry. Okay. Mo, Larry, and Curly, or whatever you want. Sometimes it's good to pick a name that means something to you, because if this is buried somewhere and you're trying to debug your circuit and you see this flip-flop called Mo, you're not going to know where was Mo. All right. But sure, you can call them whatever you want. All right, so we have the clock has to be an input here. Okay, so we have our one and only clock input, which goes to all 3 flip-flops, because that's the only place it could go. Okay, so when you write a program and you have 3 assign statements, or 3 statements where you're assigning variables to each other, you know that they don't all execute simultaneously, right? But that's not the case here. When the clock hits, each one of these is going to pass its value to the next one. And so they're like tossing a ball in the air, and each one will just catch the one from the previous one. And then they'll be stuck with it. So it's not going to go all the way through when we hit a clock. It'll just go one stage. All right. So let's in fact look at what the simulation looks like. So we have an input A, and we want to figure out the final output D. And to do that, we need to also know what B and C are. So what are B, C, and D before the first clock edge? I can't get anything past you. Right? So before the first clock edge, because I didn't tell you they were 0 or 1, you would have to say they're unknown. They're uninitialized. Okay. All right. So what happens at the next clock edge? What's 0? All of them are 0?
Just B.
Just D?
B.
B? Okay, so B will load the value that was on A, right? So B will go to 0. C is actually loading a value, but it's loading an unknown. And D is also loading an unknown. Right? So unknowns can be passed around. If your input is unknown and you get a clock edge, your output will become unknown. Okay, what happens at the next clock edge? And D is still unknown. Okay. After the third clock edge, what do I have? Okay. All right. So after 3 clock edges, I've kind of filled the pipeline, and they all now have a known value. Yes?
Actually, you finish explaining that, and then I'll ask the question.
Go ahead. I'm done.
Oh, good. So you said that you can't have the flip-flop read from a value if it's changing too close to the line?
Right.
Is there a delay or something
Yes.
on it
Yes.
writing the value? Okay.
So remember I said the output changed after the clock edge.
Gotcha. So
Not on the clock edge, right? In fact, if these flip-flops were really, really fast, we might have a problem. But these flip-flops are slow. Their output doesn't change fast enough. So by the time their output reaches the next flip-flop, it's too late.
So
They have to
read
wait.
on the clock edge, but they don't write on the clock edge.
Exactly. Well, they write internally, but the output doesn't come out.
Gotcha.
Their output will occur after the clock edge, and sufficiently after that we're not worried about it affecting anything on the same clock edge. We'll talk about this a lot. Okay, but for now this works fine because there's delay. So it's like you have 3 people in a line. They all throw the ball to the next one. While the ball's in the air, you have time to catch the previous one.
Gotcha.
Okay. All right, what happens at the next clock edge? Yeah.
The
No?
0 from A goes to B, and then everything else propagates downwards.
Okay. All right. All right. So let's just. We probably don't want to do this single step. You get the idea. Okay. So one of the things that you should notice here is B, C, and D are very similar, except C is a version of B shifted by 1 clock. And D is a version of C, again, shifted by 1 clock cycle. But B and A look different, right? Yes. And why is that? Because B comes directly from the output of a flip-flop. So B cannot change except right after a clock edge. A, on the other hand, seems to not be constrained by this. A is changing whenever it likes. And you'll see that this, for example, right here, A went from high to low, back to high, and that was completely ignored by B because B only samples A at the clock edge. So what happens before the clock edge, between clock edges, that stays in Las Vegas, okay, if you like. It doesn't matter. Only the value of A at the clock edge. Now, A has to be stable, sufficiently around that clock edge, but anything in between doesn't matter. Ignored. It's smoothed out. And this is a nice property because it gives us a nice, clean signal. If some output is coming directly from a flip-flop, it's only going to change right after the clock edge. Okay. All right. So what could we possibly use a 3-bit shift register for? Well, you might be asked to say, detect the sequence 110. So you have one input A, and you want to be able to say, hey, I just saw 1 followed by a 1 followed by a 0, where you sampled A at the clock edge. Well, this is a simple thing to do. You just need to remember the last 3 bits you saw. And that's what a shift register will do. This is the oldest. Then C is in the middle, and B is the most recent one you clocked in. So if you're looking for 110, D has to be 1, C has to be 1, and B has to be 0. And to detect this particular pattern, all I need is a handy AND gate with an inverter. Right? That gives me, G will go high whenever I have seen 110. Okay. Now, when you give a sequence like this, we kind of assume the first input we wanted was a 1, and then a 0. And this is going left to right, but in fact, this is the first input you got, so be careful with that. If I give you a palindrome, it won't matter, right? But if it's not a palindrome, then the order becomes important. Sometimes we might want to involve just the current input. So here we are detecting the same sequence, but instead of actually clocking in A, we say, oh, is A currently 0? And the past 2 are 1. And so I have that same AND gate, but now I'm using A, B, and C. Okay, so the reason I want to do this is to show you the difference between these two. All right, so this is the same simulation that we had before. You'll see B, C, and D, all delayed versions of each other. Okay, so this is G. G is that AND gate that uses the 3 flip-flop outputs. And you'll see that G actually goes high here because now we've seen a 0 preceded by 2 1s. Okay, but it's not, even though G goes high here, G is sampled on the next clock edge. It's not until the next clock edge that we realize G went high, because we're only going to look at G at the clock edge, probably. On the other hand, E, which is detecting the same pattern but based on A, it will go high earlier. So it'll go high on this clock edge. The problem with E is that it needs to pay attention to A. And so right here in this clock cycle, the previous 2 inputs are 1s. And now if A goes low, we'll see we'll see our pattern. But if A is high, we haven't seen our pattern. So E is watching A to figure out whether it has the pattern. So any change on A is going to cause a change on E. Okay, so that may be good, that may be bad, depending on what we want. But we have our response sooner. Here E went high on this clock edge, whereas G went high on that clock edge. So G will clean up the signal, but E will respond earlier. Yes?
How did E get that detection of 0 earlier?
Yeah, do you have a picture of the logic gates?
This one?
Where is E?
E is up here.
No, on the graph,
On the
in between E, there's a point where it goes to 0.
Okay, so let's look at this clock edge right here, right?
At the beginning.
At the beginning, yeah.
Beginning of E.
Oh, why is this unknown?
Why is the part
Why
next
is there a
to
part
it
not
known?
unknown?
Oh, okay. So an AND gate, you will know the output of an AND gate if any one of its inputs is 0. Remember, an AND gate will be 0 if one of its inputs is 0. So you might know the output of an AND gate, even though some of its inputs are unknown. Okay, for an OR gate, what would it be? Could you know the output of an OR gate? If one of its input is 1, then the output of an OR gate is 1. Okay, it's only going to be 0 if all of its inputs are 0. So these are controlling values. So you may still know the value of an AND or an OR gate, even though some of the inputs are unknown. Okay, so right here, let's see. Remember, we are inverting A, so we have a not A here. So if A is 1, then we know E is 0. Okay, and sure enough, A is 1 here, and that's why we know E is 0. Okay, and again, right here, A goes high, and again, we know E is 0. But here we don't know. Okay. All right. Okay. So this is the same simulation. Sometimes we will, instead of drawing out the exact pattern or the waveform, we will give the values of the signals at the clock edge. So we will just summarize the values at the clock edge, because this is a lot less work. So if you see this sequence, these are clock edges, right, the first, second, and then A is 0, G is unknown, and E is unknown, etc. Okay, so you can see here that G is delayed, responds 1 clock edge later than E. Okay. All right. Any questions on the 3-bit shift register? All right, because I'm going to talk about a parity checker next. So for the shift register, we only needed to remember the last 3 bits, say, in order to detect the pattern. Any of the bits, older bits, we could forget about. They didn't matter. Okay. In a parity checker, what we want to do is we want to determine whether we've seen an odd or an even number of 1 inputs. Okay. So the current output at a particular clock edge should depend on the current input, the input before that, all the way down to the very first input. And then we XOR them to get the parity, right? XOR gives you the parity. If you have an odd number of 1s, you get 1. If you have an even number of 1s, you get 0. So how many flip-flops do I need to do this as a shift register?
I'd assume 2, because it's got to
2?
be something finite. So you probably got something clever.
Is it finite?
1 to 3.
Is there a bound on T?
No,
No.
but there is a bound on how many parts you can fit on the chip. So
That is true. So even though I have 10,000 flip-flops, if I want to do this for 1 million cycles, I'm in trouble if I do it with a shift register, right? Not that I would want to do that. Okay. So we cannot build an infinite shift register to keep track of all the previous, but unfortunately, this XOR needs to know all of these. It's not like an AND gate or an OR gate where you can possibly figure out the output if some are undefined. Here, you need to know all the previous inputs. The thing is that we don't need to know exactly what they are. We just need to know the parity of the previous inputs. Right? If I know I had an odd number before and I know what X is now, I can figure this out. Yes? Yeah, it's a you could think of it as recursive or feedback, right? So here, with the shift register, we remember 3 bits, and that was our state, if you like. That's what we remembered. Here, I don't need to remember all exactly the bits themselves. I just need to remember their parity. And so our state here is just the parity of the previous bits. Okay. This means that I can do the following. Here's my current output is just the XOR of the current input and the previous output. So what I'm going to do is I'm going to take the current output and feed it back here, so that when the clock strikes, the current will become the past. Okay? So I will, in my state, I'm going to remember what the current parity is to use next time. Okay. So I only need one flip-flop to do this. All right.
I conservatively guessed 2. I'm glad to know it is just
Just one. Okay. All right. So let's simulate this. Okay. So what happens? What's the value of the previous y and the y to begin with? Okay, as usual, I didn't tell you it was started at 0, so they're unknown. So now, what will happen at the clock edge? You want me to go back to the circuit for a second? What happens at the clock edge? This is unknown. Do I know the output here if py is unknown? No. For an XOR gate, you need to know both inputs. So guess what happens? Still unknown. And then what happens? Still unknown. Okay. So you'll never know the output, right? And this makes sense. If you didn't initialize the parity to 0 to begin with, right? You won't know the parity. That's like a program where you didn't initialize your variables. Okay, all right. So sometimes we need to be able to initialize our variables. For the 3-bit shift register, eventually it would have filled and we would have started getting the right values. Maybe we would have had a wrong value to begin with, but eventually it would have worked just fine. This one will never work unless you initialize the flip-flops. Okay, so how do you do it? Okay, so this is what you would do if you were building your own flip-flops, but you're not building your own flip-flops. So don't do this. Okay. Basically, if you needed to, what you would do is introduce a new signal that causes the flip-flops to reset. And the way you do that is you'd interrupt the signal that's being loaded and say, hey, when R is high, load a 0, won't you please? Okay, so this will allow you to force a 0 in there with an external signal. You don't need to do this. I don't want to see anybody doing this. Because, as you know, those flip-flops have an R pin. Okay. And you can use it if you want to. All right, so they already come with an R pin. There it is. So if you want to reset your flip-flop, you can use the R pin. Okay. The other thing that I want you to realize is that on the FPGA, when it first downloads, it will reset all your flip-flops to 0 for you. So you don't even need a reset at all. You can set this to 0, and the flip-flops will still wake up with zeros. The only time that you want to use this is if, for example, during your circuit, you would like to reset that flip-flop as part of your design. say you were summing things and you wanted at some point to start over, you would want to reset the flip-flops in your adder or your counter to 0, then you would use the R pin. But if you just want them to be 0 to begin with, that already happens. You don't need to do anything. This is this global reset. Do you remember I had you connect button R in Lab 2 to something? Button R is being connected to the circuitry that's already there that causes all the flip-flops to reset. So when you push button R, you are also resetting all the flip-flops to 0. It's like you just downloaded again. Okay? So this gets your circuit back to the initial value when you just downloaded. Okay. It is possible to configure individual flip-flops to go to 1 on the global reset rather than 0. It's not the best thing to do, which I will explain. But anyway, okay. So let's assume that our flip-flop is now initialized to 0. So now I can assume it's 0. I told you it was 0. So we can assume it's 0 before the first clock edge. And basically what happens is every time x is 1, our parity changes. Okay. Now because y depends not only on the flip-flop output, but on x, you'll see y change with x. And sometimes it'll be the opposite. Like here, when x is high, y went low. Okay. So there's our parity trigger. All right. Clock enable. So we mentioned the clock enable port. So again, these flip-flops come with a clock enable. It's basically a clock enable is a way for you to freeze the flip-flop and keep it from loading. If the clock enable is low, that flip-flop will not load anything. That's not quite true. The output will not change, put it that way. If the clock enable is high, then it'll behave as you would expect a flip-flop to behave. It'll load if it gets a clock edge. Okay, so it's an additional control that lets you just freeze. So if you're using flip-flops like a register, you can use the clock enable as a signal to load or not load. All right. How do you think the clock enable is implemented? Anybody? Yes? Oh, you're no fun. All right. So usually I have some student who suggests I do this. Right? Okay. I should have asked you, Clara. Okay. Which commandment did we break? Yes. We broke 2 of them, right? We connected the clock to logic, and we connected something other than the clock to the clock pin. Okay. You don't want to do this. And you know, one of the reasons you don't want to do this is, let's say this is your clock. And this is your clock enable signal. Okay, what do you think clock enable ended with the clock looks like?
It's delayed.
What? Well, this is low, then in high. Then we go high here, and then low. And then we go high, low, high, low. Is this really what you want to feed your flip-flop? As a clock? No. If you have a little glitch here, Where should I have a glitch? Okay, if I have a little glitch here, I'm gonna get a little glitch there. This is not a good clock. Okay, you don't want this going to your, right? So, so as Marco suggested, the way we actually implement the clock enable is not to stop the flip-flop from loading, but make it just load the same thing over again. So when the enable is low, we're just going to load back the same old thing. So it'll look to you like it didn't load, but it really did load. It just loaded the previous value. When the enable is high, then we will load the data on the clock edge. Okay? So we're not really modifying how this operates. We're just controlling whether it loads the new value or the old one. Yeah?
So it kind of feels like wouldn't there be an issue with constantly just setting it back to the same value in terms of like some power consumption issue?
Yeah. No, in fact, keeping it that way would be best. The clock is, the clock goes up and down, and that consumes a lot of power. Managing clocks is a really important part of chip design in terms of managing power and speed. Okay, one that we're not worried about. We just want them to work right in 100. Okay. So what does an n-bit register look like? Okay, I just pull out, make n flip-flops. You might want to do this with a bus, and we'll talk about how to make a bus of modules later. Of course, the clock goes to the clock pin of all of them. And our load signal is just then connected to the clock enable, so that when I want to load my flip-flops, they will load on the clock edge. And when I don't want them to change, they will not change. Okay. A shift register. So this is like, we built a 3-bit shift register that was shifting on every clock edge. But if you want to control when it shifts, you just use the clock enable, and again, it will everybody will shift if shift is high, and they'll just freeze if shift is low. Okay, and this one is an n-bit ring counter. As you know, there's a ring counter to build in Lab 4. Basically, a ring counter is very much like the shift register, except that it wraps around. And we call this ink rather than shift. I could have called it shift, but what the heck are these two things for? What? Inverters. Those are inverters, but why are there inverters there? Yes? For the reset? Okay. How does that help?
Well, when you reset it, all the stored values go to 0, so then you have 1, 0, 0, 0, and it shifts 1 into like a range.
Yeah. Okay, perfect. So if I didn't have these inverters here, what would happen is when the FPGA woke up and downloaded your bit stream, all of these would be 0, and then you would be shifting zeros around. Right? There's a better way to generate zeros than shifting them around, unless you want a heater. Okay, so the idea here is that even though this flip-flop has a 0, it will output a 1. So this one is going to think, oh, this one has a 1. So you're going to be passing a 1 down here. And when this 1 comes back down here, it's going to be loaded back as a 0. Yeah?
So this is a component that counts cycles using a ring-like structure.
Yes.
It's not counting rings.
This is a counter that counts in what we call unary. right? Instead of going 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, as you would normally do, this one goes 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1. Okay, so it cycles a single 1 around. Okay. There are different types of counters. There's also a Johnson counter, which looks like this. Actually, I'm not sure it does this one. It sends a wave through, basically. Yes?
Are there any sort of practical uses for these wind calculators?
Yeah, you're using one of them in Lab 3. Yes?
So like in assembly code, when you tell a computer to rotate left, is it doing something like this?
That's a shift, right?
Or, yeah, rotate's just a shift except it loops.
It loops around, yes, right. Okay, all right. All right, do I have time for this one? No, okay. I do want, take a look at this. It's in the slides, and it's kind of important for your lab. The first thing you should know is that when you first, in a simulation, you need to wait at least 1,000 nanoseconds. In fact, I would wait 2,000 nanoseconds before starting to change the inputs, because the clock isn't going to start running right away. And there is a global reset period during which all the flip-flops are held. They won't change. Now, this didn't matter in your combinational circuits, but it's going to start to matter here. So that, I always see this, I always get a message, the simulator is not working, and what invariably I see is that the simulation was only for the first 1,000 microseconds. It didn't go any further. So your sequential simulation will only start to actually behave at basically 1,000 to 2,000 microseconds. Yeah?
How come there's such a big gap where clock is the value at 0?
Because this is held as 0. During the first 1,000 nanoseconds, it is simulating the startup procedure of the chip. Okay, so it made that part of its simulation. Okay, when you weren't using flip-flops, you didn't care. But now you're using flip-flops, so you do care. Okay, the other thing is later clocks are going to be more complicated, and they're going to start later. If you start at 2,000, you're safe. Okay. The other thing I want you to notice is that we have 3 different types of reset. This one is preset. Even though this one is initialized to 1, it will go to 1 on the global reset. But if you try to reset it yourself, it will not go to 1. So this only works for the global reset. You are better off using this, the 2 inverters, if you want to be able to reset it to 1 yourself. Okay. All right, that's my last slide. I'll see you all Monday.